Alright, in this video we're going to get some more practice working with double integrals, and I really think these are great problems for visualizing what's happening in the region that you're integrating over. So what we're going to do here is you're given this double integral here, and we're going to compute it by reversing the order of integration. Now, why would we want to do that? I mean, it would be good practice, is kind of working with these things, but looking at the way this is written right now, the first thing I would need to do was to integrate this with respect to x. So this y would be a constant here. No, I'm just going to write this down out here like this without the bounds. I don't really care about the bounds right now. But if I'm thinking about this and I'm integrating with respect to x, I could even think about this y as a constant. I could even move it outside here. So let's just concentrate on this integral. How would we do this? All right. The short answer is we cannot. We cannot do it. We could try to do some u sub. If we let u be x squared, then du would be 2x dx. And we could certainly introduce a factor of 2, but we cannot introduce a factor of x. So we cannot integrate this the way that it is. Now, if I was integrating this thing with respect to y, if I was doing this integral with respect to y, dy, now I could do it, right? Because that's a constant. I could think of moving this outside of there, and I could do it. No problem. But I can't just switch these willy-nilly because I have these bounds to contend with. This bound of y squared to 9 is for x, and this bound of 0 to 3 is for y. I can't just switch these. It's not going to work like that, okay? Because remember, we would have to write, if we switch these would have to be functions of x, not y. Okay, so kind of an interesting problem. But if we can get them switched, it's going to be a lot easier. So the first order of business here is to visualize the region that this iterated integral is integrating over. We need to figure out what that region is. And then we can think about how we could switch the bounds. Okay, so let's look at this inside piece, this inside integral. It's telling us that x is going from y squared to 9, and it's telling us y is going from 0 to 3. You think you could draw a graph of that region? I think you should try. All right. So if I know my x is going from y squared to 9, I mean, I could put this 9 out here. That's great. But this is some x equals y squared. All right, what does that look like? Well, if I took the square root of both sides, I'd get this. And I'm in the first quadrant here because y is going to go from 0 to 3. So that is fairly easy to write out, 0 to 3. Okay, so if I graph y equals the square root of x, let's see, 1 is going to be about 1, square root of 9 is 3, so it's going to kind of look like this. So let's think about which way this is being cut, right? This y is out here, so we know that this y was fixed. So the way this integral is being written, the cuts are going this way. And my x's are going from the graph y squared to 9. Right, like that. Awesome. From here to here. Okay, and then I'm summing up my y's. I'm summing up these slices from y equals 0 to 3. So from the information given to me, this is my region. Now, once I have figured this out from the information in the integrals, now I can think about switching the order, right? So now we want to switch the order of the integral, and we want to do our slices this way, fix x. So we can fix some x out here, and then we'll put our dy in here. Okay, so I'm going to let you think about this now. maybe pause the video and see if you can figure out what these, put that in there, what the bounds would be. All right, well, let's look at our generic slice right here. And this slice is going from some y value up to some other y value. All these slices are going to start at 0, and then they're going to go up to this graph, which was y equals the square root of x, or x equals y squared. So the y value is going to range from 0 up to the square root of x for our slices going this way. And then we're going to add up all these slices going from x equals 0 all the way up to 9. So you can see how different these bounds are, right? You really need to look at the picture and get an idea of what's happening. All right, so I'm gonna go ahead and compute this. This is something hopefully you're getting better at. So if you want to pause the video and work it out, I'll start it once I have this red part done and talk about it, and then pause it and do the green part. All right, so for this inner integral, this red part, you should have gotten 1/2 x sine x squared. Okay, so now what we need to do is integrate that business from 0 to 9 dx. All right, so if you want to pause the video and give that a try, you can. If you want to, I'm going to talk through this one a little bit. You might want to fast forward if you think you've got this. So this one involves a u substitution. I kind of alluded to it earlier. So if we let u equal x squared, then we're going to get du equals 2x dx. So we need a 2x dx. Well, we've got an x, so I might think about, I'll bring this half out here, 0 to 9, and I'm going to rewrite this x dx. So then I could put this 2 in here and then balance that out with a half out there. Now, you could integrate it right now and just keep everything in terms of x, or if you want to change your bounds and write it in terms of u, you can. So I think I'll show both ways. If I do the u sub, I'm going to have 1/4 integral. Now I need to change my bounds. So if this is x is 0, I'd put this in here. Maybe I'll write it over here. So to change my bounds, for x equals 0, u would be 0. And the upper bound of x equal 9 would turn into u equal 81. So I would have to change my bounds to go from 0 to 81, and then I could just write sine u du. Okay, and then I could do this integral fairly easily. 1/4 negative cosine u from 0 to 81, which would give me negative 1/4 cosine of 81. That's very weird. Minus cosine of 0, which is 1. And then that would be negative, so I think we'd end up with plus 1/4 there. Okay, so that's one option. Now you don't have to turn it all into u's. You could just come over here and integrate it with respect to x and leave your bounds how they are. So you'd have 1/4 the integral from 0 to 9 of, well, I can just integrate it now. I don't have to have that in there. So the integral would be then negative cosine of x squared, and then all this business would go away. That's your du part. And then do this from 0 to 9. So then I would have negative 1/4 cosine of 81 minus, put the 0 in there, you'd get 1, negative 1, negative 1/4, minus a negative, you get the same thing. Okay, so whatever you prefer. Just a little review of the u sub. All right, let's try another one of these. Compute the iterated integral by reversing the order of integration. So first notice the order that it's in right now, we'd have to integrate this with respect to y, which looks a little yucky. If I could switch this order and integrate with respect to x first, this would just be a constant, and that would be super easy integration. Okay, so I'm going to encourage you to pause the video and look at these bounds and see if you can draw a graph of the region that we're integrating over. All right, so I think the best way to start this is to think about what you're fixing. So we're fixing some x, so we know our slices are going to be vertical. So what these bounds are telling you, let's go, what these bounds are telling you are the lower and upper bound of your slice. All right, so for this fixed x. So we know we have to go from e to the x up to e. So I drew these graphs of y equals e to the x and y equals the constant of e. So those are the lower and upper bounds of your slice. All right, so now it says x is going to go from 0 to 1. Now, how do you know that it's going to stop at 1, like at the exact right place? Well, it doesn't always, when I say exact right place, it's the point of intersection of these two graphs. It wouldn't have to be that way. I mean, we could, I don't know why they always do that a lot in these examples. I guess I could have switched it. We could have gone to 0.75 or something. That's fine. That would have meant that our region would have just, say, stopped somewhere at 0.75, and we would have to draw some boundary for our region, and then our region would have only gone to here. But because the integral told us that we were going from 0 to 1, well, let's see how far over that is. If I find the coordinates of this point of intersection, when x is 1, well, if I put 1 into this equation right here, e to the first, I get e. So the ordered pair 1e represents this point of intersection, which is handy. It isn't always going to work out that way. I just want you to know that. But it does give us this region that's completely bounded by these two graphs in the first quadrant. It's not cut off anywhere. Okay, awesome. So now we have this bounded region. Now we need to think about how it's going to work if we cut it the other direction. Okay, so if you haven't done that already, go ahead and do your slice the other way. Do your slice horizontally and see if you can rewrite this integral. Basically, you're just figuring out the bounds. All right, so if we slice the other direction, let's say we slice, this doesn't really matter where we put this, we're going to fix some y. So all these horizontal slices, right, start at 0. Okay, so that's easy. All these horizontal slices start at 0. And they end over here. They're over here on this curve, y equals e to the x. Okay. So I just changed the color of this to make it a little easier to read. So now remember this, with this dx here, we need this upper bound to be some function of y. So I need to write this equation here, y equals e to the x. I need to solve that for x. So it's in terms of y. All right, how are we going to do that? Good job. I heard some of you say it. We're going to take the natural log of both sides, or rewrite it in natural log form. And you're going to get natural log of y equals x. Okay, so that means our upper bound then is the natural log of y. Great. Okay, so now these slices, what is my lowest x value? So these, or sorry, y value. I'm going to do my slices now, my dy. What is my lowest y and my highest y for my slices? My lowest y starts at 1, and my highest y slice up here is going to be when y equals 3. E. Sorry, I was looking at that 3. E right here. So, all right, so 1, 2, E. 1, 2, E. Okay. So that was a lot of work to get there. That was good, but now it's going to pay off when I do this integration because it's going to be very easy with respect to x because that's just a constant. So I'm going to go ahead and work out this red part, and then I'll start the video when I have that done, and I encourage you to do the same. All right, well, didn't that turn out nice? Okay, so remember, this is just a constant, so the antiderivative of this is just that constant times x, and then we're going to put our upper and lower bounds in for x. So I put natural log y in for x, so I get y natural log y times natural log y. Those just cancel to give y. And then when I put 0 in here for x, that all wipes out, and I just get y. Awesome. So now I'm going to put y up in here for this red part and do the integral from 1 to e y dy. That should be pretty quick. 1 to e y dy. All right, there we have it. So that integration was very, very easy. I mean, relatively, comparatively easy because I was able to switch these bounds.